Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for joining us today for best practices for extrusion coating surface treating. If you have any questions during the webinar, please use the GoToWebinar question tool. You may submit a question at any time during the webinar. We'll reserve time at the end of the presentation to answer as many questions as we can. Please note this webinar is being recorded, and you'll be able to access both the recording and presentation slides once they are available online, usually within 24 hours. In today's presentation, we're going to cover the basics of extrusion coating, why surface treatment is used, how your application defines which technology is best, where treatment is used on extrusion coating lines, and the importance of web handling. And again, we'll wrap up with our Q&A session. Today's presenters are globally recognized as two of the most knowledgeable experts in the field of surface treating. Tom Gilbertson is Enercon's Vice President of Application Engineering and has over 35 years of surface treating experience. Tom has authored numerous technical papers and articles on surface treatment, including chapters in TAPI's Extrusion Coating Manual. And Tom is a frequent presenter at industry events, including TAPI Place, AMCAL, SEMA, ICE USA, and the Flexographic Technical Association. Mario Leonardelli is Enercon's Vice President of Engineering and OEM Product Manager. Mario works closely with OEMs to integrate Enercon surface treating solutions seamlessly into their lines. Mario has nearly 30 years of experience with leading international extruders and converters. With that, I'll turn it over to Tom, who will begin by talking about some of the basics of extrusion coating laminating.
Thanks, Mark. Good morning, everyone. I hope you're all doing well, or good afternoon, depending, I guess, on where you are. I appreciate you joining us today for this presentation on best practices for extrusion coating surface treatment. So, extrusion coating and laminating technology has been around for a long time. It's used exclusively or principally in things like industrial packaging, also used for food lamination, things of this nature. And it has some very interesting characteristics, and it does a great job relative to its particulars, depending on, of course, what it is you're trying to create. The properties and performance of these composites as compared to adhesive lamination are quite different. You know, adhesive laminates are used for also used for all kinds of food and industrial packaging, but extrusion coating applications are more varied. They're more complicated, therefore they can be used in more demanding applications. So I think you're going to enjoy this webinar as we do our travel through the process. Next slide. So examples of extrusion coating are many, and what we selected here on this slide are just showing a few. And they can range from anything as sophisticated as constructing a particular film product or barrier product for a medical application, all the way down to something that may be more industrial, like, say, wrapping for lumber, you know, for an example. But the one common theme among all those applications are the fact that we are using extrusion coating technology to either coat the main film or we're using it as an adhesive in order to create a barrier layer that then is used in a food or liquid packaging. You know, one of the more common ones that everybody seems to know today, we all have various experiences with this, are the sort of soup or juice in a box type of products. You know, where you go to the grocery store, you can buy your favorite brand of soup, for example, in a box that's all shelf stable, and it can sit out there for the longest time. If you have children, grandchildren, whatnot, and you purchase these juice products in a box, really it's the same thing, just in a smaller format. In any event, those products are used for the ability for those products to be shelf stable. You don't need refrigeration, so that product can sit on the shelf for a long time. And its construction involves multiple substrates different types of substrates and combining them and interfacing them so that they provide the necessary water vapor and air barrier to make sure the product inside stays safe and secure. Next slide. So extrusion coating really comes in two flavors. Sometimes it can be, the terminology can be used interchangeably. There are instances where extrusion coating is just what it sounds like it is, meaning I unwind a primary web and I apply, let's say, a polyethylene extrudate to that outer surface. And that might be used for something as straightforward as barrier protection. Maybe you're making a single-sided product that you just need some weather protection on the outside of that product, and that polyethylene that you put out there is used for that. The other type of extrusion coating involves lamination, and that would be where the extrudate, like in my first example where you're using it just as a coating, that actually extrudate now is used as an adhesive, and you can then use that and combine two other structures on the other side of that. So you could have like a paper, the polyethylene, and maybe a foil, let's say, as a structure, and the extrusion coating portion, that polyethylene in between those two products, is then used as a means of adhering the paper, let's say, and the foil in that case. So to get a little deeper into this, we'll look at the next slide and we'll see a bit of an overview of kind of what this looks like. So in this picture, you see the main substrate, that orange substrate coming into the chill roll and the nip area, and you see where the extruder is. And that extruder is actually taking these polyethylene pellets, melting them, and applying them into this nipped gap area so that the substrate product actually gets coated with that polyethylene extrudate. And so again, this material is then can be used for all manner of things. And that layer is sort of compressed and squeezed and forced into that, let's say, the paper product for the main substrate. And it just creates this this product that is very useful and helpful in ongoing applications downstream. Next slide. So you can do multiple things with these now. You can just envision, if you think the last slide and you had multiple extruders on this line, you could do all manner of different sort of unwinds and combinations, maybe up to 4 or 5 different operations all in one bypass, one passing through the line, which would give you then a tremendous durable product at the very end. The one common thing throughout this presentation that we're going to focus on today is we are going to focus on the fact that the extrudate layer here typically is polyethylene. Now that doesn't mean that it's always that or it can only be that, but the polyethylene extrudate in this example, in this presentation example, is primary. That's kind of the normal version that was used in the course of constructing these various products. Next slide. So how do we optimize all this? How do we make sure that that extrudate is thoroughly affixed to either the primary substrate, or if you're going to be using it as an adhesive in a lamination application, how do you make sure that all this goes together and then stays together? Let's take a look. So when you want to optimize the adhesion in your process, you will look for surface treating equipment in varieties of locations along the context of the line. So for example, we unwind a primary substrate. That substrate typically has to be surface treated prior to its first introduction into the process. Now, that primary treater could be a corona treater. The primary treater could be a gas flame treater. Depending on what your primary substrate is, that may determine really what piece of equipment goes in that primary treat position. So let me give you an example. If you're running board stock and the board stock's sort of a typical product in nature, meaning that it has some fibers on top, it's a little rougher surface. In that instance, you may find that in that case, it's better off to flame treat that, because the flame will sort of burn those fibers away so that when it passes into the extruder, you don't get any of those fibers poking through the extrudate. On the other hand, if you're unwinding a film, let's say just a standard film product off there, and you're going to extrusion coat onto, say, a polyester film, you could use a flame treater. That would work too. However, it may be better for you in that case to use a corona treater for other reasons. And that corona treater would adequately treat that primary substrate, prior to it going into the extruder. Now, if we go take a step forward, so follow with me as I go, to the right here on this slide. So let's just say, for an example, we have another unwind here, and this other unwind now has the ability to introduce yet again another secondary web into the process. So we're going to go from an extrusion coated product to an extrusion laminated product. So that secondary unwind now comes off, goes through yet another surface treater. So let's just say, again, as an example, we're going to unwind some foil. We're going to treat that Class A foil so that we thoroughly clean it, get any remaining oils off that foil before it gets down into the nip area to where we extrusion coat the other side. Now I kind of have let's say a paper, poly, foil lamination that I just came up with. Let's just, for the heck of it, go one step even further. Let's say we have a third unwinder out there. We could actually unwind yet again another substrate and introduce another extruder into this equation and come up with even a bigger substrate that has multiple layers and capabilities to it. But then finally, once we get the structure we want, we've got it all tied together here, we unwind it. Before we wind it back up at the tail end of the machine, we may want to post-treat this. We may want to add treatment on the outside of this product such that in your next operation, whether it's at your place or at your customer's place, that surface has been treated such that they can do something to it. Maybe they have to decorate it. Maybe then it even goes through another lamination process, who knows. But point being is it's prepared for that next step. Now I'm going to focus a little bit on one other area here that's important, because we're going to touch on this as we go through the presentation. And if you look carefully into that nip area, you're going to see a terminology in there called ozone. And ozone treatment is a very interesting technology. It really is what it sounds like. We generate ozone gas, specifically generate ozone gas, and we apply it right at the nip point of the extrusion process. So the extruder is dropping the extrudate down into that nip area, and at that same juncture, we then gently apply ozone to that extrudate. Now you might ask, well, that sounds great, but why are you doing that? I thought ozone was bad for us. We don't want that in the plant or anything. Well, that's true, but ozone has some really interesting properties in this particular application point. Ozone is highly oxidative. So when it hits that molten polyethylene extrudate, it oxidizes the surface such that the surface now has a great deal more affinity, bond strength to the web with which it's being entrained. And it can provide some real benefit. And we're going to get into the details of this going forward, but I wanted to make sure that you were aware of that little detail. You might have missed it in the slide, and it's right smack there where the arrow is. And as I said, we'll continue more on this as we go ahead. Next slide. So why do we have to treat films anyway? In our last slide, you saw that we have a main unwind and we go ahead and we surface treat it before it goes into the extruder, or for that matter, we now have a product, and before we wind it, we decided, hey, I got to treat this product before I wind it back up. So why do we have to do that? Well, polyethylene, basically polyfilms in general, whether it's a polyethylene, polypropylene, polyester, any of the sort of normal films that you're familiar with, by their nature, they have a very low surface energy. There's really nothing on the surface, no polar groups, there's no activity, nothing there to allow a coating or an ink or adhesive or something to wet and stick to the surface. In addition, a lot of these poly products have surface contamination. It could just be from storage, it could just be from the air, or it could be from migrating additives that are already baked into the structure of the film. So at the end of the day, what this means is the surface of that product is really not suited to allow for wetting at all. And so we need to treat this surface in order to bring that surface tension back to an area where it will be more receptive to wetting a liquid. Next slide. So you could also look at it this way, right? The film comes to the treater in a manner where you have all this baggage meaning like additives and surface contamination and maybe even some age to it. Maybe the surface of the material's been, because of its age, it's got a bunch of crystals on it. Just, it's just not really suitable for converting. You couldn't really get any sort of adhesive coating, whether it's extrusion coated or even a standard adhesive coater. You couldn't really get that chemistry to work on that surface. And what the corona treater does is removes that baggage from the surface, cleans it, functionalizes the surface so that in the converting process, we're all set to go. Next slide. So if you look at this slide, pictures are worth 1,000 words, right? You can see what happens when we surface treat these polymer products. So when we unwind a film, let's say, going back to our previous slide there, where you saw the film coming off the unwind, we unwind that material, we surface treat it. What are we actually doing? Well, you can see in the picture, that inside picture in the slide, what actually happens here. We go from a surface that's not wettable to a surface that is wettable. And this is a key thing, a key point that I want you to really grasp, and that is your surface treater, whether it's a corona treater, flame treater, plasma treater, whatever that is, that technology that happens to be on your line, that is the purpose of that treater. The purpose of the treater is to get the surface prepared so it will wet a liquid. And this slide, does a great job of illustrating that and makes it easy for you to see. Next slide. Next slide. So up next is my colleague Mario, and Mario is going to talk about the types of surface treatment that are used in the extrusion coating process. Take it away, Mario.
Thanks, Tom. I appreciate it. Hi, everyone. What we like to go over is the specifics of your application, which determines which surface treatment technology should be used, where you could have a flame treater, a corona treater, and as Tom talked about, have in line an ozone generator on your line. Next slide. The specifics of your application determine which surface treatment technology should be used. So based on the information we receive and based on what kind of technology you're familiar with, we'll decide and quote you which system would be best for your application, if it's a flame treater, if you want an ozone in line with the corona treater, etc. So based on the information we get from you, that would determine the specific technology we would use. Now, Tom went into a lot of details regarding the typical schematic that we have here on the extrusion coating line slash extrusion laminating line. Basically, like he said, on the primary unwind here, you could have a flame treater or a corona treater. You could have a corona treater in the secondary or post treat for future printing on the extrusion laminator, etc. Next slide. So the one scenario that came up is we talked about possibly having a flame treater coming off the primary unwind, especially if you're treating any type of paper, craft paper, paperboard, etc. Because what you want to do is you want to burn off those fibers so that you get a nice coating as you apply it prior to the extruder, so that you don't have any pinholing and cause any damage to your next process if you don't burn off those fibers properly. Well, the benefits of a flame treater, and a lot of times, if you're not familiar with the flame treater, you probably don't want to use it. Is a little more complicated than a simple corona treater, but people use it specifically for paper applications, and very high line speeds so that you can get a higher treatment level. You can avoid backside treatment, which is caused by having air trapped behind the web and the roll. You avoid pinholing the film, and you don't have to worry about ozone or any kind of other solvents or UV emissions that may occur when you have a plasma treater, corona treater. Now, the flame treater, when you consider one, is designed with a high velocity drill port or a ribbon burner. You can have it as a mass flow or volumetric control. The line speed is a big determination if you should use flame treating or not. Obviously, if your line isn't running as fast, running 200, 300, 400 feet per minute compared to a 1,200, 1,500, 2,000 feet per minute, flame treating is probably not your application because obviously you got an open flame and you could do some damage to your plastic film and your paper. And the other consideration when you're talking about flame treating or corona treating is the cost of the system. The flame treater is quite a bit more expensive and a little more takes a little more care to take care of the flame treater. The second scenario, as we discussed and Tom touched on, you could have a corona treater on the primary unwind. And the reason, and that's probably the most common type of surface treatment used on an extrusion coating line for converting process, is a corona treater because it's less expensive, it's easy to use. Operators don't have much to worry about when you're dealing with a corona treater. It is the most optimal choice, and it does its job. It increases the surface energy that Tom discussed to increase your adhesion. Next slide. So here are the basic components of a corona treater. You have a power supply, you have a high voltage transformer, which then steps up the voltage to about 10,000 points. And in that air between the gap between the electrode and the ground rail, what we do is we ionize that gap with an electric field to generate a high electric field so that you can create corona. And that's basically a real simple schematic of a corona treater. Now there are different options on a corona treater that you can get. You can get a covered roll system, which consists of a metal electrode and some kind of dielectric on a roll, or you can get a bare roll system or a hybrid of a bare roll system, which is what Enercon calls a universal roll system, which is a ceramic roll, which includes on top of a ceramic electrode. Now, as I mentioned before, a covered roll system, which is one of the more basic and original corona treater systems out there, been around for a long time, is just a metal electrode with some kind of dielectric on the roll, which could be a Hypalon cover rubber roll, a vulcanized silicone roll. More common is a ceramic roll or a silicone sleeve roll. So you got different various coverings that you can put on the covered roll system. The other thing you can also do is you can lane treat. So you can decal the treatment across your film if you like. And the only drawback with a metal electrode system is you can't run any type of non-conductive films, meaning you can't run aluminum foil or a metallized PET because you would create a short circuit between the electrode and the ground roll. The bare roll system, or what we call at Enercon is a universal roll system, it's more of a uniform corona treater. So if your treat width is 1850 and you only want to run a 900 millimeter wide web, you're going to create corona across an 1850 millimeter treat width, and you can run any type of film across there at any width. You can run any type of material. You can run metallized film, not have to worry about adjusting any segments, etc. You can run aluminum foil through it. So it's a little more easier for operators to control. The universal roll sieve that I mentioned before is our ceramic electrode with a proprietary covering on the ceramic roll, and it allows us to get higher treatment level, to keep the footprint of the station smaller, and it helps against getting backside treatment, which usually occurs when you get air behind the web and you ionize the backside of that web. It helps avoid pinholing, and it helps reduce wrinkling. Tom, go ahead. I think this ozone generator. Tom will discuss that more in detail.
Thanks, Mario. Appreciate that. So we're going to get back onto the ozone treatment in the extrudate, which is a technology that's been around for quite some time and is extraordinarily beneficial relative to the use of getting the adhesion between the extruded material and the main web to be what you want it to be. So if we do a little closer view of this, on this slide you can see we have, again, our extruder, the die, and then the extrudate. And let's just say, again, for the sake of this dialogue, we're going to talk about the extrudate being a polyethylene material. And again, if you look in that little interface between the nip roll and chill roll, you can see this little blue dot, which is supposed to represent an applicator for an ozone generator. And so what that applicator is it spans the entire width of the die, and then it is connected to a device that actually generates ozone. So if we get into the next slide, you can we'll start getting a better view of what all this equipment looks like. So the cabinet that you're looking at in front of you is actually the power supply and the houses the power supply and the cells that generate the ozone. And inside that cabinet are the various components required to then create this ozone gas, which will then get vented out through tubing from this to the applicator. And the whole benefit of this is we can get much better bond adhesion profiles between the extrudate and the primary substrate. And because of it, that then can allow us to do things like lower our die gap. We can potentially lower than the extruder temperature. When we're doing all this, then usually production speeds can increase, which then add value and economics to your product, right? So not only did we make it stronger, but we did it faster, and we did it in a way that is more beneficial to the end use of the product. So ozone generators can be immensely beneficial in these applications. Next slide. And here's a great picture. This is an awesome picture of just what this little applicator looks like in context of all the various parts that are here. And so that applicator where the arrow is pointing spans the entire width of this particular application. And we are, blowing is the wrong term, but we are actually sending ozone gas out of this applicator, and ozone being heavier than air, it wants to fall into that gap. So where we have this little pocket, you know, where the chill roll and the nip roll meet, you have this little pocket that's in there, and the ozone just kind of falls inside that pocket and sits there. And while it sits in there, it's oxidizing that extrudate, continually oxidizing the extrudate such that it now has an affinity to the primary substrate. And so when you do a peel adhesion test afterwards, and you do one, you know, compare it with ozone and without ozone, most of the time that will afford you a real benefit relative to peel adhesion numbers. Next slide. So how does this work? Well, really, it works like this. The ozone generator takes compressed air from your facility. We treat that air through a membrane. We dry it to a very, very low dew point. I've had this question a lot over the years. People say, well, can't I just take the ozone I generate from a corona treater and, you know, kind of bundle it up and send it over to the extrusion coater? And it would be great if it worked that way, but it doesn't work that way because ozone is not as effective when it's just in its atmospheric condition. You know, when you exhaust it out of your treater, you have whatever the dew point is in the air and the dirt and the debris and so on and so forth. Well, when we purposely take air and we compress it, we dry it to like a minus 20 or 30 or 40 dew point, and then we send it through these generation tubes that then take that dry air, create the ozone, and then send that ozone out to the applicator, where it then is dispensed right into the nipped area between the chill roll and the nip roll of the extruder. It does a great job, and this little illustration gives you a good understanding of the flow of how this all works. Next slide. So let's back out again. Let's kind of recover where we just were. So again, you can see where the applicator is in the photo, and then if you look to the left, you can get an understanding of where the applicator is, you know, schematically, right? So depending on the application and certain details, that applicator has a particular angle that you're going to address it to, and you may tilt that applicator downward a little bit, just to again allow that ozone a nice, direct, and easy path to sort of fall into that gap area. And we're doing this, by the way, without moving the curtain at all. The extrude is not affected whatsoever relative to this gas in terms of moving it, and certainly not doing anything relative to affect the temperature of that extrude. So it really is a tremendous application benefit without really any negative impact whatsoever. Next slide. So how do you optimize this setup, right? What's the best way of using it to the best that you can? Well, really one of the first things you have to understand is ozone is best used when the extrude is a polyethylene. That just tends to be the way it works. Now, I've been involved in all kinds of applications. We've tried different extrudates. You know, sometimes you get some benefit. The benefit isn't quite as great, but I can tell you this, generally speaking, when the extrude is a standard polyethylene and we're looking for better peel adhesion numbers, ozone is really a huge benefit there. Next slide. So here's an example of this, right? So you can optimize your entire operation, your entire extrusion coating experience can be optimized by using ozone. We kind of touched upon it earlier, right? So if you use ozone in this example, you can positively affect your production rates. By using ozone, you may be able to, drop your die gap. If you can drop your die gap, that means you can modify your die temperature, reduce that. By doing that, then that may mean you can run the line faster. Further, let's talk about more specifically about a given application. Let's just say, for example, we're building a package here that's used in a food product, right? Well, all those things we just talked about, lowering the die gap, adjusting the temperature, things of that nature, those can be very impactful relative to food packaging. If your die temperature is too high in a food package, you always run the risk of imparting a certain taste or odor into that package, which of course is, a non-starter. You can't do it. Sending ozone into that area can be quite beneficial at not only preventing that from happening, but then giving you all these other benefits. And here's a great example of this, right? So you can see as we change speeds, what we actually can do here relative to the gap between the between the extruder and the gap where the extrusion meets the primary substrate and where the applicator for the ozone generator is. It can be very, very effective relative to line speed and air gap. So as you can reduce your air gap, typically your line speeds go up. It is not uncommon after these units are in place to hear people speak of improvements in terms of throughput improvements by 20, 30. I've actually had a few examples over the years of 50% improvements. And here again, you can see in this slide, if you add yet one other step, so let's say we have our ozone applicator in there, it's doing its job, but maybe we also added a surface treater that's treating that main substrate prior to it getting into the application. It can be really impactful, right? And you can see it on the chart with no treatment versus just ozone treatment. And then when you add corona treatment on top of that, your adhesion profile is tremendously improved, right? Which also leads me to a point that I get asked from time to time. People say, well, can't I just ozone treat it? Can't I just take a substrate and pass it through an ozone treater and then put it in the extruder process and see if that doesn't work? Well, that doesn't work. The ozone treaters are really only used for the specifics as we've discussed here, that being they're used in a manner to put ozone onto a molten extrudate. They don't really work relative to treating a pre-made film. Next slide. So yeah, again, here's a great example. Ozone Corona, it will improve your adhesion profile really without doubt, and it really can be improved even further as you add these other surface treatments in addition. And when you stack all this together, and then you take into account that you can run your lines faster, you can drop your die gap, you can then drop your temperature of your die. These are all very, very powerful tools that you have at your disposal now to really increase your productivity and provide your customer with a better product. So now let's talk a little bit about,
Tom,
go ahead, Mark.
Hey, Tom, it's Mark. Mario's got a little bit of a technical issue with his audio, so if you want to finish up here with web handling.
Okay, that's great. Thanks, Mark. So, okay, so how do we deal with the film as it's going through the system and make sure that it is in the right location, right space, no sort of film problems as it goes on and about its way? Well, let's start with the treater. We want to make sure that when the material's going into that Corona treater after an unwind, that the treater is aligned properly, so therefore the web has no wrinkles, and that the substrate is thoroughly under control and flat on the treater roll, which then leads to the question, well, do I need a nip roll? Do I need a nip roll to help control that web against the treater roll? Well, if your substrate is heavy and you have a high web tension, such like paperboard, just heavier films, for example, where you're actually able to have some web tension on that material without any negative impact, then of course nip roll probably isn't really necessary. Now that may change. That could change a little bit if you or your OEM partner decided to use the treater as an in-feed pull roll on that line. If that's the case, then regardless of what I just said, then the treater's got to have a nip roll, right? That just makes common sense. If the substrate is a film and the speeds are high and you have very thin gauge film, then typically a nip roll is recommended. And people will ask me, well, what speed is that, Tom? How fast do you have to go before you start thinking about it? Well, in my experience, I started looking seriously at incorporating nip roll designs in our treaters when you start getting in that 700, so foot per minute or higher. And when you combine that with a gauge of film that's very thin, so if you're running 0.5 mil film, let's say even less than 1 mil film, and you're running 700,000-800,000 feet a minute on a consistent basis, then we really start having that conversation about the use of the nip roll in a surface treater. And again, if the treater is in question, if it's being used as a pull roll type of setup, then a nip roll is required without respect to any of that. Next slide.
All right, thanks, Tom, and thanks, Mario. Before we get to questions, and I do see we have some out there, and please feel free to use the question toolbar to submit your questions. We'll get to as many as we can. And just a few points to review. Extrusion coating success is dependent on your adhesion results. That's the true measure of success. Pre-treatment is used in several different areas on an extrusion coating line to optimize adhesion results. Your application, the type of film or paperboard that you're using, the line speeds that you're running, all combine to help determine which surface treatment technology is best to use. Ozone is proven treatment method at the extrudate, and it can provide significant production benefits in both bond strength as well as operational benefits relative to speed and temperatures. And proper web handling is critical. You always want to have your substrates presented to the corona treater flat and without wrinkles and under control. And if you're using high speeds or using the treater roll as a pull roll, often a nip roll is the best way to go. With that, we'll now switch over to some of the questions. All right, so first question is, which treatment method would allow the extrudate to adhere to ink on a printed film? We have tried lamination grade inks without success.
Well, for treating a film, you could use really any sort of corona treating method should work. Now, like in all these things, the devil is in the details, and I'd be happy to dive into that with the questioner here if they would like to connect with me offline. But general answer to that question is, if you corona treat that surface, you should be able to get to where you want to go.
Another question is, it was mentioned that adding ozone oxidizes the extruded film. Does this create air bubbles or pinholes in the film?
It does not. It does not affect using ozone does not affect the extrudate at all. So the extrudate is totally unaffected by the use of ozone, and so you don't have to worry about the ozone creating any sort of wrinkles or waves or pinholes or any sort of defect whatsoever.
Do you need to exhaust the ozone at the application point?
That's a great question, and the answer to it is no, you don't. And the reason for that is, if you think about it for a minute, ozone is a very unstable molecule and it has a very short half-life. So it'll start recombining at temperatures, 350, 400, it'll start breaking down. Well, if you think about what the typical die temperature is on an extrusion coater, 500, 550, 575, those numbers are big. So really, you don't have to worry so much about having to deal with any ozone that escapes. First of all, we're applying it in a way that it really doesn't escape. It doesn't get out into the area where people are. It stays pretty confined within the context of the extruder. If you do have decals on your die and you have to, you're adjusting your width from something wider to something narrower, the ozone applicators also have decals on them. So you can match that to the decal on your die such that you don't have ozone being placed in an area, say, where there's no extrudate.
We have a question. What's the methodology to tell if the ozone treatment is actually providing any benefit?
Well, the number one way to do it is just peel adhesion numbers. So if whether you're using an Instron or however, whatever test equipment you have in your lab, the best way to do it is take some samples of material that you created prior to the use of ozone. You might have some retains or something, or data that you already know. Look, we have these kind of peel adhesion numbers, and then contrast and compare them to samples that were done with an ozone generator, and you'll likely see some pretty significant benefits. Now, many of you are familiar with a lot of the OEM partners that we have. Many of those OEM partners have laboratory equipment. Of those, some have ozone generators in their laboratory. You may talk to your resin suppliers. Some of our resin suppliers that are out there also have ozone equipment in their labs. So if you want to do some trialing going forward, check out those sources. You may not know it, but some of your friends that you're doing business with now may already have this equipment that would afford you the ability to do some lab testing.
Tom, this is a question that doesn't have a specific material mentioned, but it says, is it possible to get dye levels higher than 42 to 45?
Well, it depends on the material. So let me give you an example here. So let's say we have a polypropylene material. It's inherently in the low 30s, and we can usually treat that material on the extruder up to easily 40 dynes, maybe 42 dynes. If you took a polyester film and you applied the exact same power density to that polyester film as to the polypropylene film, you would see the dyne level go up into the 50s. Nothing changed, right? We used the same power value on the polypropylene example as I used on the polyester example, yet the dyne level was increased by 30%. And it's not really a function of the equipment in that case, or the function of kilowatts. It's really more the functionality of the surface of the material. So as these different materials, whether they're polyester, polypropylene, polyethylene, polystyrene, whatever they all have their own affinities towards these surface treating methods. And so therefore you will see different outgoing dye numbers as a result of that. So depending on what substrate you're working with, you may see numbers higher than 40 or 42 dynes. It just depends on the material.
We have a couple of questions about the use of ozone treatment outside of the NIP. For example, would ozone treatment work to adhere the extrudate to, well, in this case, it's a little different, the extrudate to paper instead of flame or ozone? Would ozone treatment work to adhere the extrudate to paper instead of flame?
No, it really wouldn't. I think
it meant or Corona.
Yeah, I get this question. It's a great question, and I understand why you asked it. It just doesn't, the ozone doesn't really have any affinity to the base substrate. I remember doing a trial many years ago where we had an ozone unit set up in our lab, and we weren't doing it with paper. In this case, we were doing it with film. But we thought the same thing. We thought, well, what if we built a little box, we put the ozone applicator in there, and we exposed the film to ozone, while it was kind of immersed in this box. And what we learned from that experience was really we just filled the box in the room up with ozone. It didn't do anything relative to the performance of the film. So, short answer to your question is I'm afraid not. The ozone doesn't seem to, at least in our experience, doesn't seem to do anything there.
Is there any evidence of ozone being effective if the extrudate is only 20% polyethylene?
Another really good question, and I would suggest that, and that's a pretty detailed question. I would suggest that that you have a conversation with your resin supplier there. I'm not going to go through a list of names here, but the many resin suppliers, all the people that you guys know, have a lot of data that they've collected over time relative to the effects of ozone and the various blends of polyethylene relative to the extrudate. So if it's a polyethylene EVA combination or whatever it is, they can help you sort that question out, I think. And if they can't, maybe you're coming up with something they haven't tried before, then that would be a good opportunity to do a lab trial with them and sort of sort that detail out directly.
Tom, this question could go in a couple different directions. Do we have a table of comparing the analysis of a contact angle ink droplet versus the treatment dyne level measurement?
We don't. Now, I will again give you a little historical reference here. Some years ago, we did a 24-month comparative test between a goniometer, this sort of grandfather device for measuring contact angle, with actual dyne testing. And we did the test comparing this droplet test of distilled water versus the solvent, standard at the time, solvent style dyne fluid. And while there were instances where we could get some comparative numbers, they were never consistent, and certainly not consistent between different film types. So we came to the conclusion that each test has a benefit. The testing your surface energy, testing your surface of a product using a contact angle device can have its own benefits for your process, but also discrete dyne testing also can have some benefit by testing in your process. And it's not that they don't have benefit in each case, but they don't necessarily share the same benefit. So they may not be co-joined data, right? They're two separate data points that you can use to track your process variables as you go forward. So that's really how we look at it today. When we do dyne testing, we do dyne testing for the purpose of dyne testing. When we do contact angle testing, same thing. We're doing it solely for the purpose of contact angle testing.
We have a question here. Generally speaking, what dyne level can be achieved on LDPE using a post-corona treater?
Depending on the polyethylene, what additives are in there and so forth, but I think it's quite safe to say that you can easily achieve low to mid 40s without any issue whatsoever relative to treating that material prior to it being wound up, and really not have any difficulty whatsoever. If you would happen to have a product that had a lot of additive in it, maybe a lot of slip content, some anti-block, things of that nature, you might need a little more power to get there, but I still think you can probably get there at the rewind.
What type of treater technology would you recommend for a polypropylene non-woven lamination?
Well, it depends on some things. Speed and the type of non-woven. So depending on the thickness of the non-woven and the speed of your application, there may be a few ways that we could go. Certainly, a Corona treater, universal style Corona treater would likely be the first stop in this journey. We would look at that as the first place. If for some reason, due to maybe the nature of the non-woven, meaning its thickness, or some variations within the scope of that product, if that's not suitable for that type of treater, then we could look at some other versions of that treater or augmentations of that system to go ahead and to treat the material. When we do these presentations, and this question leads me to this point. Excellent question. So when we do these presentations and we explain these different types of surface treating equipment, people can understandably come to the mind that, well, a Corona treater is just like this, and there's these certain variations of it, and that's it. Believe me or not, there are variations within variations of Corona treater design, and so there are things that your OEM, your manufacturer that you choose to use for Corona treating equipment can do for you to help modify that equipment or adjust that equipment in such a way to be to work very well with a non-woven, or with let's say a embossed film, or something that's a little less commonplace. You just need to share that with them on the front end, and then they can do the right thing for you.
All right, looks like we've got a couple more questions. Is the ozone solution used to reduce the LDPE hard odor in extrusion coating? In this case, their final product is a metallized BOPP sealable film.
Well, it certainly can be. I mean, think about it. If you can drop your die gap in your example, and that might allow you to drop your die temperature, and even if it allows a minor die temperature reduction, and right now maybe you're on the verge of some taste and odor issues. I mean, that one solution could really do wonders relative to fixing that problem. So again, the devil are in all these details, and I recognize we're in the format where that's not possible to dig into that, but it is certainly possible. It is something to consider for sure.
Does ozone affect peel values from using hot melt or water-based adhesives differently?
I'm not exactly sure I understand the question. In our conversation today, we're talking about the peel adhesion values of between the extrudate and the primary substrate, if the substrate's whether a paper or whether it's another film. So really the peel adhesion values I'm referring to there all relate to the adhesion between the extrudate and another substrate. That's really what we're talking about today.
All right. Thank you, Tom. Thank you, Mario. And thanks to our audience today. If you have any additional questions, you can certainly reach out to Tom and Mario. They'd be happy to help you, whether you're looking to set up a trial or just to get some more information. We'll be sending you a link with the recording and the presentation slides within 24 hours. If you found this webinar beneficial, please let us know. If you have ideas for topics that we should cover in the future, let us know that as well. We appreciate your time joining us today, and that will conclude today's webinar.